talk about continuity, ladies and gentlemen, let's suppose we have a real number, and that number is in the domain of C. Informally, the function of f is what we call continuous. At a particular x value, if you can draw the graph of f, and near the point C, which again is just an x value, you can draw the graph without lifting your pencil. We say it's continuous. So in other words, if I have to draw my graph, it stops, lift it up, and continue drawing it, then we say it's not continuous at that particular x value. So we say if you can just simply draw your whole entire graph without lifting your pencil, then we say it's continuous at C. That's just kind of the informal definition of when we say continuous. Now that we know more about limits, the true definition of continuity is going to deal with a limit definition. So it is continuous at a particular point, provided that these conditions are given. First of all, the limit as x approaches C has to exist. So in other words, you have to find the limit at that particular x value. F of C exists, meaning that particular x value has to be in the domain. So if a number is not in the domain of a function, then we know it's not continuous at that particular number. And then the third and final condition is that the limit as x approaches C has to be equal to the defined value. So these are the three things you always have to check when we are talking about being continuous at a particular x value. If you remember back from Unit 8, we talked about different types of discontinuity. So remember, there are two types of discontinuity that we talked about back in Unit 8. One was removable. We talked about back in Unit 8 what removable discontinuity is. And remember, that occurs when you had a hole. And that's as much as we really talked about removable discontinuity. Remember, that means that when you factored, so for example, if you had a function x minus 3 over x squared minus 9. Remember how we found if you had a hole at that particular function. Remember, we factored the numerator, factored the denominator. And if you had that common factor appear in the numerator and the denominator, you knew you had a hole at x equals 3. So if you remember, we knew that the hole happened when you had that common factor in the numerator and in the denominator. Now, in definition of our limits, when we talk about continuity, we talked about the three conditions that have to happen. The limit has to exist, f of c has to be in the domain, and the limit as x approaches c has to be the same as the defined value. Now that you know the definition of limits, this is how you know when you have a hole. The limits are the same. So in other words, the limit from the left is the same as the limit from the right. However, what creates the hole is that this will not be equal to f of c, or f of c is not defined, meaning that c is not in the domain. So when we are checking to see whether we're continuous at a particular x value, and if I ask you the type of discontinuity, we know it's going to be removable if the limit exists at c, but it's not equal to the defined value, or c is not even in the domain. So that's removable discontinuity. Non-removable discontinuity. So non-removable discontinuity, again, we talked about non-removable meaning that you have the vertical asymptote. There's actually two subcategories of non-removable discontinuity. Again, infinite is what we talked about back in Unit 8. That means you have a vertical asymptote at a particular x value. There's also what we call jump discontinuity. So a jump occurs, and really what you'll be looking at for a jump is when you have a piecewise function. A jump discontinuity happens when the limits are different on the left and on the right. So if you graph it, notice the limit from the left would be here, but the limit from the right would be here. So that's what we call that jump discontinuity, because literally you have to jump from one part of the graph to the other to get to the other part. But that's all classified as non-removable discontinuity. Like I said, the infinite discontinuity occurs when you have a vertical asymptote. All right? So like I mentioned, just to review here, the function is continuous if you have the following conditions. This means that C is in the domain, so f of C is a number. It is defined. The limit as x approaches C from the right is the same as your f of C. And the limit as x approaches C from the left is also equal to the defined value. And these are like proofs. A lot of times, ladies and gentlemen, I'm going to say, we're continuous at 2. Show me that it's continuous at 2. So it's like a proof. You've got to justify it using these 3 conditions. So anytime I talk about continuity, you must show me or justify the continuity now that you know what continuity is by the limit definition. So a lot of times I'm going to tell you it's continuous at a number or it's not continuous at a number. You've got to show to me or prove to me why it is or it isn't. All right, so let's take a look at an example here. So determine if the function is continuous or discontinuous. If it is discontinuous, categorize it as a type. There's a direct connection between continuity and domains. So if a question is asking you about continuity, find the domain. Because if you tell me the domain is all real numbers except x equals 5 and 3, well then right away you know it can't be continuous at 5 and 3. So you know exactly where the discontinuity is going to occur. So first of all, let's take a look at A. What kind of function is x squared plus 1? It's a quadratic. It's a U shape, correct? Do you have any holes in a quadratic graph? Do we have any holes? No. Do we have any vertical asymptotes? No. Do we have any jumps? So is there any place where this function is going to be discontinuous? No. So then we know it's going to be continuous. And it's continuous for all real numbers. Like I said, you're looking for holes, you're looking for asymptotes, you're looking for jumps to find discontinuity. So any questions on A? Now let's take a look at B. You have a rational function, you have a fraction. Well, what makes a fraction undefined when you have what? 0 in the denominator. So I need to figure out where I'm going to get 0 in the denominator. So I can factor x squared minus 9 into x plus 3 times x minus 3. So I know the domain's going to be all real numbers except what? Domain's going to be all real numbers except what? 3 and negative 3. So where is it going to be discontinuous? It's going to also be discontinuous at where? X equals what? 3 and negative 3. If the numbers are not in the domain, it's not going to be continuous at those numbers. So any questions on why it's discontinuous at 3 and negative 3? Now the question is, what type of discontinuity do I have? Well, what's happening graphically at 3 and negative 3? Do I have a hole or do I have a vertical asymptote? Vertical asymptote. So if it's a vertical asymptote, I call that, remember, your infinite discontinuity. You can always call this the non-removable as well. Again, depending upon the textbook, depending upon if you're taking the SAT math question, some will not use the phrase infinite discontinuity, they'll just use non-removable. Some will call it infinite discontinuity, but just know infinite discontinuity is a subcategory of your non-removable. All right, so any questions on B? So I have infinite discontinuity at 3 and negative 3. So again, I have another fraction in part C. So I know that anywhere I get 0 in the denominator, I'm going to end up with discontinuity. So when I factor x squared minus 9, that factors into x minus 3 times x plus 3. So now, where is it going to be discontinuous? It's going to be discontinuous at what two x values? What? 3 and negative 3. Now be careful, we're going to have two different types of discontinuity. What's happening graphically at x equals 3? You're having a what? A hole. So at x equals 3, when you have a hole, what type of discontinuity is that? Removable or non-removable? Removable. At x equals negative 3, you have what? Not a hole, but at x equals negative 3, you're going to have a what? Vertical asymptote. So then at x equals negative 3, I know that that's going to be infinite discontinuity or your non-removable. So any questions on C? So now let's take a look at D. So again, I've got two fractions here. Again, I know that I could combine this into one single fraction, but what's the least common denominator going to be here for these two fractions? Your least common denominator will be what? X and x plus 3. So again, I know if I was to add these two fractions together, I would end up with an x and an x plus 3 in the denominators. Do you agree with that? So then where's the discontinuity going to occur? The discontinuity is going to occur where? At x equals what? Negative 3 and 0. Because remember, you have the x on the bottom. So we have discontinuity at negative 3 and 0. So any questions on how I know it's going to be discontinuous at negative 3 and 0? Now the question is, graphically, do we have holes or do we have asymptotes? Unfortunately, the only way to verify that we're going to end up with asymptotes or holes is you do actually have to add these together to one single fraction, because to see if we can reduce it. So again, remember, I'm going to have to multiply the first fraction by an x plus 3. The second fraction, top and bottom, gets multiplied by an x. So I end up with 4 times x plus 3 plus 3x squared, all over x times x plus 3. So when I distribute the 4, I end up with 4x plus 12 plus 3x squared, all over x times x plus 3. So now the big question comes into play. Can you factor that numerator? Because if you can factor that numerator and you end up with a factor of x plus 3 or an x, you know you have a hole over a vertical asymptote. So the question is, can I factor 3x squared plus 4x plus 12? No, you can't. So then what's happening graphically at negative 3, 0? Do I have a hole or do I have an asymptote? Asymptote. So that I know I'm going to have infinite discontinuity at x equals negative 3 and 0. You know that it's not going to be continuous by just looking at the denominators. But the problem is you don't know if it's a hole over an asymptote until you actually simplify that numerator and see if you can factor it. All right, so any questions on how we end up with infinite discontinuity at negative 3 and 0? So now let's take a look at a piecewise function. So remember, when you have a piecewise function, you have multiple functions in the same function. Each function has a restricted domain. So when you're given a piecewise function and you're trying to talk about continuity, look first of all at each individual function. So look at 2x minus 1. Graphically, if I was to graph 2x minus 1, this is going to be a what? A line. So you agree with me, if I graph y equals 2x minus 1, it's just a line. Do you have any holes when you graph a line? Do you have any vertical asymptotes when you graph a line? Do you have any jumps when you graph a line? No. So now take a look at the second function, x squared plus 1. What type of graph is that? It's a quadratic. It's a U. Do you have any holes in the U? Do you have any vertical asymptotes in the U? No. Do you have any jumps in the U? No. So the only way, if there was going to be any place that this piecewise function was discontinuous, it's going to be where the domain is restricted. Because we don't know if this piecewise function is actually going to connect at 0 or not. We don't know that. If let's say that when I go to graph 2x minus 1, x less than 0, I end up with that part of the graph to be up here versus this one being down here, I may have a jump at x equals 0. So that's what I have to check for. So now remember, what I'm checking for is I want to check to see if continuous at x equals 0. Because you already told me that x squared plus 1 and 2x minus 1 does not have any holes, any asymptotes, or any jumps anywhere else in the graph. So we need to check at x equals 0 to see if it's going to be continuous or not. So first of all, what you have to do, remember, to check for continuity is you have to find the defined value. So tell me what f of 0 is equal to. Where would I plug 0 into, the first function or the second function? Second. So what is f of 0 equal to? F of 0 is equal to what? 1. So now you have to find the limits. You need to find the limit as x approaches 0 from the right, and then you need to see if it's equal to the limit as x approaches 0 from the left. Well, I already found what the limit as x approaches 0 from the right is going to be, because I already plugged 0 into this second function. So what is the limit as x approaches 0 from the right? That's just going to be what? So it's going to be 1. The question is, what's the limit as x approaches 0 from the left? So now I have to plug 0 into my first function. And when I plug 0 into my first function, what's that output going to be? -1. So is the limit from the left equal to the limit from the right? No. So is it going to be continuous at 0 then? No. So it's not continuous. So it's discontinuous at x equals 0. So any questions on how I know it was not continuous at 0? So now the question is, what type of discontinuity is going to occur? Well, with the limit from the left is not equal to the limit from the right, is it going to be removable or non-removable discontinuity? Non-removable. And what type of non-removable discontinuity? Is it going to be a jump or an infinite? Jump. So I have jump discontinuity, which is, again, your non-removable. That's what creates the jumps in the graph, when the limit from one side is not the same as the limit from the other side. That's what's going to create that jump in the graph. The piecewise function will not connect. All right, so any questions on C? All right, again, we can skip over letter F. All right, we'll do a couple other examples and we'll come back to F. So now let's take a look at another example. And this is what I was mentioning before. Sometimes I'm going to tell you it's continuous at a number. So show. Anytime they say that word show, that means it's like a proof. I'm telling you it's continuous at -3. So again, you've got to check all three conditions. First of all, you have to find the defined value. So you have to find the defined value. That's one condition. So I'm going to plug -3 in for x. So -3 plus 1 over -3 minus 5. So that gives me -2 over -8, which is 1/4. The second part is you have to find the limit. So you have to find the limit as x approaches -3 of f of x. Well, how do you find limits? You just took a quiz on limits. What do we do, first of all, to find limits? You try and find limits by doing what? Direct substitution. So I'm going to plug -3 in for x. -3 plus 1 over -3 minus 5. And again, since I'm telling you that it's continuous at -3, you better end up with the same number. And then finally, for part C, f of -3 has to be equal to the limit as x approaches -3. Which again, we know that 1/4 is equal to 1/4. You must show and you must state all three conditions. Again, it's a proof, just like you had to do back in geometry. I told you it's continuous at -3, now you're proving it to me, and all three conditions have to be true. Therefore, we know we are continuous at x equals -3. Okay? So your conclusion is, now that you've found all three conditions to be true, we know that it is continuous at x equals -3. So any questions on how you can show continuity? Again, yes, you just end up plugging in -3 multiple times or plugging in that particular x value. Okay? So any questions on that one? Let's take a look at example 3. Decide if the rational function is continuous at the given values. If not, specifically state why. So again, I'm giving you two different x values. Part A is when x equals 2. Part B is when x equals 5. Well, first of all, I'm going to go ahead and factor this denominator, which is going to give me x minus 4 times x minus 2. So again, you've got the three conditions. So the three conditions for continuity, remember, is first of all, you want to find f of 2. What happens if I plug 2 into this function? Is 2 in the domain? Is 2 in the domain of this particular function? Is 2 in the domain? No. So is f of 2 defined? No. F of 2 is undefined. You don't have to do anything more with the continuity definition. You already know it fails the definition of continuity. All right? Since f of 2 is undefined, we know it's not continuous at x equals 2. Again, 2 is not in the domain. In order to be continuous, the number has to be in the domain. So there's no point. You don't have to check and find the limit. We already know it's not in the domain. So now the question is, what kind of discontinuity is happening at x equals 2? Do you have removable, non-removable? What kind of discontinuity is at 2? It's removable. Okay? You guys go ahead and do B for me. Again, check all three conditions again. Tell me what f of 5 is. Tell me what the limit as x approaches 5 is going to be. And then tell me if f of 5 is equal to the limit as x approaches 5. Again, if it fails any one of those three conditions, it is not continuous. Yes, Tegan? Yes. Yep. Yep. You can. Yep. All right. Again, you've got to check that f of 5 is in the domain. And when you plug in 5, we know we end up with 1. Again, you can simplify the fraction. Once you know there's a hole at x equals 2, simplify it, make your life easier, and just use 1 over x minus 4. Again, when you find the limit as x approaches 5, we end up with 1. And again, we know that the defined value is the same as the limit. So therefore, we know it's going to be continuous at x equals 5. So again, you've always got to show those three conditions. Like I mentioned, there is a direct connection between continuity and domains. So anytime I'm asking you about continuity, the first thing you need to be able to do is find the domains. Just a review of some of your domains. Where are polynomial functions continuous? You took a test back on Unit 8. Polynomial functions are continuous where? Is there any place where polynomials are not defined? No. Remember, they're continuous for all real numbers. Remember, a polynomial function is like an x, x squared, x to the third, and so on. Rational functions are continuous at every number that's in its domain. And remember, the domain is going to be all reals except where your denominator equals 0. So rational functions are continuous, remember, at all real numbers except where your denominator is equal to 0. So they're going to be discontinuous at those x values you get in the denominator. Again, next unit, Unit 10, which is our last unit, we'll be studying our exponential and log functions, which I know you guys did in Algebra 2. But just remember, except where the denominator equals 0. I just abbreviated. Except where denominator equals 0. Exponential functions are continuous for all real numbers. Remember, an exponential function is when you have a 2 to the x, a 3 to the x, a 4 to the x. It's where the x is an exponent. Log functions are continuous at all x's greater than 0. Remember, when you have a log function, you cannot take the log of a negative number. Whatever's inside the log has to be greater than 0. It's been a while since we've graphed sine and cosine. But thinking back, way back, when we graphed sine or cosine, did we have any holes? No. Did we have any jumps? Did we have any vertical asymptotes for sine or cosine? No. So remember, sine and cosine are continuous at all real numbers. Again, negative infinity to positive infinity. When we graph tangent, however, remember, tangent of x, you did have vertical asymptotes. Remember, at tangent, we had a vertical asymptote at negative pi over 2 and positive pi over 2. Remember, that's what your tangent graph looks like. Remember, so between your two vertical asymptotes, tangent is continuous at every real number within its asymptotes. So again, from negative pi over 2 to pi over 2, tangent would be continuous. So anywhere between the asymptotes, tangent would be continuous. So now let's take a look at a graph. So now, for example 4, determine if the function is continuous, and then if it is not continuous, state the type, and then justify your answer. So first of all, given this graph, tell me a place where you think it's going to be discontinuous. Give me an x value where you think it's going to be discontinuous. Negative 3, I agree with that. Why? There's an asymptote. So what kind of discontinuity do we call asymptotes? That's going to be a what? Is it removable, non-removable, jump, or infinite? It's going to be non-removable, and then more specifically, it's going to be an infinite discontinuity. And again, the justification is f of negative 3 is not defined. Where do you have another place? At 0. And what kind of discontinuity do we have at x equals 0? Jump. Now, what's my justification? How does it fail that definition? Because 0 is in the domain. So f of 0 is defined. How does it fail the definition of continuity? What's happening? Limit from the left is not equal to what? Limit from the right. So the limit as x approaches 0 from the right is not equal to the limit as x approaches 0 from the left. Which, remember, if these two values are not the same, then the limit as x approaches 0 of f of x does not exist. Because remember, we're checking to see if the two-sided limit exists, if the two-sided limit is the same as the defined value. So since the limit from the left is not the same as the limit from the right, the two-sided limit does not exist. Is there any other place that this graph is going to be discontinuous? Do you have any other holes? Do you have any other asymptotes of the graph or any other breaks or jumps? No. So now you guys go ahead and just review. Go ahead and find those limits for me down there at the bottom. Review of what you just did on the quiz.